All right, let's set the scene. You are in the boardroom.
Right.
The air conditioning is humming, the coffee is probably stale, and you are staring at a projection screen that is making everyone in the room sweat a little bit.
And we're not talking about quarterly earnings.
No, not at all. We are talking about liability. Specifically, the liability of a machine making a life or death decision at 130 kilometers per hour.
And not just any machine. We're talking about the core architecture of the vehicle itself.
The fundamental nervous system of the car.
Exactly.
So for today's deep dive, we are role-playing. We are stepping into the shoes of senior tech strategy consultants,
Okay, I like it.
our client. You're looking at engineering directors, chief architects at the world's biggest OEMs and tier 1 suppliers, the people who are right now losing sleep over the year 2026.
And for very good reason. I mean, 2026 is the year the training wheels really come off.
They're gone.
We are moving from the era of fail-safe into the era of fail-operational.
Now, that sounds like buzzword bingo, I know, but the distinction is actually terrifyingly specific.
It's critical.
So our mission today is to deliver a strategic report, a McKinsey-style MECE that's mutually exclusive, collectively exhaustive analysis of how to survive this pivot.
And we have a massive stack of intelligence to synthesize here. We're looking at Electrobit's product strategy, specifically some of the analysis from Lucien Badescu on a software-defined reliability.
Right.
We have trend reports from AVL on battery health, simulation data from AD Dynamics, and we're looking at the whole global regulatory landscape.
Yeah.
From the UN all the way to China's new GB standards.
So the objective is crystal clear. Deliver a roadmap for the fail operational vehicle. Because if you're an engineer listening to this and you are still designing systems that just, shut down when they break,
Then your product is already obsolete.
it's worse than obsolete. In the context of level 3 or, say, level 4 autonomy, it's downright dangerous.
It is. It's a liability waiting to happen.
Okay, so let's unpack that immediately. This is part 1 of our report, the strategic paradigm shift. Why is fail-safe no longer an option?
To really get this, we have to look at the old world, which is basically everything on the road today up to, say, SAE level 2. So think of your current lane-keeping assist system.
Okay, yeah. I'm driving. I took my hands off the wheel for a second to open a water bottle. The system is steering.
Correct. Now imagine the electric power steering motor overheats or maybe a sensor glitched out.
And what does the system do right now?
It beeps aggressively. A big red light flashes on the dash and the system disengages.
It turns off.
Right, it turns off.
It enters what we call a passive state. It fails safe. The core engineering assumption, the axiom, is that there is a human hot standby right there, behind the wheel.
You are the redundancy.
You are the redundancy. The machine fails, you take over, and it all happens in milliseconds.
Which is fine, at level 2, because I'm legally required to be paying attention anyway. But we are talking about the 2026 roadmap. We are talking level 3, level 4, and that is where the tire logic completely breaks down. In level 3, especially under the new UN R157 regulations, allowing speeds up to 130 km/h, the driver is allowed to be eyes off.
Eyes off. You could be checking emails.
You could be watching a movie on the center screen.
Sure.
The car has accepted liability.
So if that steering chip fries at 130 kilometers per hour and the system just fails safe, meaning it shuts off, I have, 0 seconds to react?
Less than 0.
I'm looking at my phone and suddenly the car becomes a 2-ton unguided missile.
Precisely. The human reaction time to look up, to assess the situation, grab the wheel, and correct the trajectory it's just too slow. You will crash before you even process that the system has failed.
So the paradigm has to shift. It has to become fail operational.
Right. The system cannot shut down. It's not an option. It has to detect the fault, it has to isolate it, and critically, it must maintain operation stay in an active state long enough to execute what's called a minimum risk maneuver.
An MRM.
The MRM.
Minimum risk maneuver. That sounds very sterile for what is essentially please don't kill us.
It's a very polite term, yes. It usually means pulling over to the emergency lane and coming to a very controlled, safe stop. But to do that, the steering has to still work. The brakes have to still work.
The sensors still need to see the lines on the road.
Everything must keep functioning, even after the primary computer has, literally caught fire.
I think the best way to visualize this urgency is to use the steer-by-wire case study. This is really the catalyst for all of this, isn't it?
It is. This is the hardware reality that's forcing the software strategy to change. In a traditional car, you have a steering column, a big steel shaft.
Right.
Even if your power steering motor dies, you are still physically connected to the rack. You can muscle the car over to the side of the road. Physics is your ultimate backup.
But the OEMs, they want to get rid of that column.
Oh, they desperately want to. It takes up space, it causes vibrations, and in a crash, it's basically a spear aimed right at the driver's chest.
And with the new skateboard EV platforms, they want that design freedom to put the cabin anywhere, so they have to cut that mechanical link.
And you're left with steer-by-wire, just a cable carrying data from the wheel to the rack.
And this is the so what for our client, for that director in the room. If you cut that mechanical link and your single wire breaks or your single ECU crashes,
You have no steering.
none. The wheels might lock in their current position, or maybe they just caster freely. Either way.
You hit the wall. It's as simple as that.
So redundancy isn't a premium feature anymore. It's not an option on the spec sheet.
It is the ticket to play. It's the absolute baseline for survival, and the market drivers are enforcing this. You mentioned UNR 157, but we have to look at China.
China is being extremely aggressive on this, the GB standards.
Specifically, GB 44495 through 44497. These are mandatory national standards coming into force right around that 2026 timeframe. They're explicitly requiring event data recording and, crucially, safety rollback mechanisms for autonomous functions.
So if you're a German OEM or an American OEM and you want to sell in the world's biggest car market,
Your architecture must be fail operational, period. End of story. There's no way around it.
and then you have the commercial side of things, the robotaxis.
Yes, Waymo, Cruise, Zoox, for them, it's an OpEx issue. It's about operating expenses. Their key metric is availability.
Right.
If a robotaxi detects some minor sensor glitch and performs an emergency stop in the middle of a busy intersection, which is a classic fail-safe reaction, what happens?
It causes a traffic jam. It needs a human rescue team to come get it.
It loses money. Every minute it's stopped, it's losing money.
So they need the car to be able to, at the very least, limp home or limp to a safe parking spot to protect the business model.
Exactly. So what you have is this perfect storm. You have a regulatory push from governments and a commercial pull from the industry leaders.
It's a pincer movement.
It is. There's no escape.
Okay, so that sets the stage. Now, let's move to part 2 of our report, the software architecture strategy. This, you said, is where most engineering teams get it wrong.
This is the first and biggest trap. We call it the two fail-safes fallacy.
I want to drill down into this because it seems so intuitive on the surface. Why can't I just buy 2 cheap computers, maybe duct tape them together, and just say if A breaks, use B?
It sounds perfectly logical, right? But it fails the MECE test. It leaves huge, dangerous gaps. Let's just walk through it. Imagine you have 2 identical ECUs sitting side by side. ECU A is driving the car.
Okay,
Suddenly it fails. A chip fries.
no problem. Switch to ECU B.
How?
Well, the system switches over.
Let's just, if ECU A is completely dead, who or what tells ECU B that it's time to take over? You need a third thing, an arbiter.
A voter.
And that voter now becomes a new single point of failure.
You got it. So, okay, you say I'll make a really robust voter, but that's not even the biggest problem.
What's worse? Synchronization and state. This is the real killer. Let's say ECU A has been tracking all the objects on the road for the last hour. It knows the velocity of that truck in the next lane. It knows the friction coefficient of the wet road. It knows everything.
It has a complete world model.
Complete high-fidelity world model. Suddenly it dies. ECU B wakes up from its slumber. Does ECU B have any idea where that truck is?
If it was just sitting there cold? No, of course not. It has to boot up, initialize its sensors, and look around.
And that takes time. It could be milliseconds. It could be seconds. At highway speeds, that blind time is fatal. You've created a gap. This is the classic split brain problem in computer science.
You can't just glue 2 computers together. You need something more intelligent.
You need software-defined redundancy. The redundancy has to be managed at the application layer, not just by having spare hardware sitting around.
So a safety manager.
Exactly. You need a safety manager module. This is a serialized software layer that runs on both chips, or maybe on a separate microcontroller, and its only job is to constantly synchronize the state of the vehicle between the 2 systems.
So it's passing notes back and forth constantly.
Constantly. It ensures that if A drops the baton, B is already running at full speed and knows exactly where the finish line is. There's no gap.
This brings us to a really fascinating detail in the Electrobit strategy that I saw. It's the resurgence of Classic AUTOSAR.
Yes. I love this detail because it's so counterintuitive to the whole Silicon Valley narrative. Everyone is talking about software-defined vehicles, and they immediately think high-performance computing. HPCs.
Right, Adaptive AUTOSAR, Linux, QNX, these big, powerful, complex operating systems.
Because you need them to run the AI models. You need massive compute for perception and path planning.
For the brain of the car.
For the brain, yes. For planning the path, for spotting the pedestrian, for deciding to turn left. By all means, use Linux. Use Adaptive AUTOSAR. But for the muscle,
The actuation.
the actual command that sends voltage to the steering motor or pressure to the brake caliper, you absolutely cannot use Linux for that.
Why not? Is it just too heavy, too bloated?
It's too unpredictable. It lacks what we call hard real-time determinism. In a general-purpose OS like Linux or even QNX, the scheduler might decide to pause your critical steering task to do some garbage collection for another process.
Or handle a logging thread or something less important.
Right. And that pause might only be 20 milliseconds. It sounds like nothing.
But 20 milliseconds at 130 kilometers an hour?
Is a very noticeable and dangerous jerk in the steering wheel. Or worse, it's a missed deadline for a critical safety check. For the muscle, we need worst-case execution time guarantees, WCET.
We need to know with mathematical certainty
That no matter what else is happening on the chip, the brake command will execute in, say, 1 millisecond. Every single time.
And only Classic AUTOSAR or similar bare metal real-time operating systems can provide that rock-solid determinism. So the winning architecture, the one that survived 2026, is a hybrid. It's an AI supercomputer on top, acting as the brain, giving orders to a dumb but incredibly reliable Classic AUTOSAR underling that actually moves the wheels.
Dumb is maybe unfair.
Let's call it disciplined.
Okay, discipline.
It's the difference between a creative jazz drummer who is fluid and improvises and a metronome. You want the metronome driving your wheels. Just tick-tock, perfect timing every time.
Let's talk about how we protect this system. We have this concept in the standards, freedom from interference, FFI.
This is a huge pillar of the ISO 26262 safety standard. Imagine you have your fancy infotainment system running on the same hardware cluster as your safety monitor.
Which is the direction everything's going, right? Domain consolidation.
It is. So the user is streaming a 4K movie, and the video player app, which was written by a third party, crashes.
The blue screen of death.
Right. Now, if that crash is allowed to corrupt the memory space that's being used by the braking algorithm.
You have a catastrophe. That's interference. That's a catastrophic interference. So we need firewalls.
Software firewalls?
We need safety firewalls. And they come in two main flavors, spatial and temporal isolation.
Okay, let's break this down for the client. Spatial isolation.
Spatial isolation means using a memory protection unit, an MPU. It's a piece of hardware on the chip that strictly forbids App A from writing to or even reading from App B's assigned memory addresses. It's like having separate locked offices for different departments. You can't just wander into accounting and mess with the books.
I see. And temporal isolation.
That's all about time. It's about access to the CPU. We use watchdogs.
Watchdogs.
Yeah. If the infotainment system starts hogging all the CPU cycles, taking too much time and starving the safety app, the watchdog notices it's exceeding its time budget and forcibly kills it or puts it in a lower priority state.
So it guarantees the safety-critical app gets its turn on the processor no matter what.
It guarantees its slice of time. It prevents a non-critical function from causing a timing failure in a critical one.
This all sounds incredibly complex, which leads to the buy versus build discussion. If I'm a strategic consultant advising a major OEM, building all of this rigorous safety software from scratch, it sounds like a 5-year nightmare.
It is, and you don't have 5 years. You have until 2026. This is where the concept of COC comes in, safety element out of context.
Okay, explain the business value of COC. This is key for the directors in the room.
Traditionally, you certify your safety software for a specific car. This is the brake software for the 2026 Model X. You do all the testing, all the documentation for that one context. It's incredibly slow and expensive.
Right.
ACOC allows a supplier, like an Electrobit, to build a generic safety module, say, a communication stack or an OS, and certify it generically out of context.
Like a pre-approved certified building block.
Precisely. They certify it based on a set of assumed inputs and outputs. They say, if you give us X, we guarantee to produce Y within Z milliseconds with ASIL D compliance.
Yeah.
The OEM can then buy this pre-certified block, drop it into their architecture.
And they inherit the certification.
They inherit a huge chunk of it. It can reduce the ISO 26262 certification effort by, in some cases, 50%.
So it's really a time-to-market hack.
I'd call it a survival strategy. It allows the OEM to focus their precious engineering resources on the unique AI features, the secret sauce that differentiates their car, instead of reinventing the wheel on basic safety protocols that are, frankly, becoming commoditized.
Okay, great. So we've designed the software stack. We have our safety manager. We have our disciplined classic AUTOSAR metronome. Now, part 3, the hardware and network implementation, the physical layer.
This is where things get heavy and hot. Let's start with the nervous system, the network.
The old CAN bus is dead, right? Or at least it's on life support.
It's not dead, but it's been relegated to the cheap seats. You'll still use it for, window motors and seat controls, but for the critical data backbone steering, braking, sensor fusion, we're moving to Ethernet.
But not the Ethernet you have in your office wall.
No, absolutely not. Standard Ethernet is best effort. It sends a packet, and if it gets there, great. If there's a collision, it waits a random amount of time and tries again.
And best effort is not good enough for a brake command.
Best effort kills people in cars. We need deterministic Ethernet. And for our fail operational use case, we are specifically using the 802.1cb standard.
Which is also known as FR. That's frame replication and elimination for reliability.
I love FRR because it's such an elegant, almost brute force solution. It solves a complex software problem with simple, robust hardware.
Okay, walk us through the signal path. The brain says turn left. What happens?
The brain ECU sends that turn left packet to a special TSN switch. The FRER logic in that switch instantly duplicates the packet. It sends copy A down wire 1, say, along the left side of the car, and simultaneously sends copy B down wire 2 along the right side.
So we have 2 physically separate redundant paths.
Right. Now, the receiving switch at the steering motor is listening to both of those wires. Let's say copy A arrives first. The switch accepts it, validates it, and passes it to the motor controller. 1 microsecond later, copy B arrives.
Does it process the command twice? Does the car jerk left twice?
No. That would be very bad. The switch hardware looks at the sequence ID of copy B, realizes it's a duplicate of a packet it has already processed, and just destroys it. It's eliminated.
So what's the real advantage here?
The magic happens when a wire gets cut. Let's say a piece of road debris flies up and severs wire 1.
Okay.
Copy A is lost. But copy B, on the other side of the car, is completely unaffected. It still arrives on wire 2. And because both were sent at the exact same time, there's 0 delay. There's no timeout and retry logic like you have in TCP/IP. The stream of data to the motor is completely uninterrupted.
That is seamless. It's beautiful. But a nervous system needs blood. It needs power. If the battery voltage dips for even a moment, all those computers crash.
Absolutely. This is the dual board net requirement. You cannot, under any circumstances, rely on a single 12V lead-acid battery anymore. You must have a primary and a secondary power source.
And the secondary is usually a supercapacitor or maybe a small dedicated lithium-ion unit?
Yes, but just having 2 batteries isn't enough. The real challenge is managing the fault isolation. And this brings us to the death of the humble fuse box.
The rise of the e-fuse.
The smart fuse. Think about a traditional fuse. It's just a piece of metal designed to melt when it gets too hot.
It's primitive, really.
It's slow. It relies on thermal inertia. By the time the metal filament actually gets hot enough to melt and break the circuit, a dead short might have already pulled the entire system voltage down to 6 or 7 volts for a few milliseconds.
And for a sensitive microprocessor, 6 volts is good night. It triggers a reboot.
Exactly. At 130 kilometers, a reboot is not an option. An E-fuse, on the other hand, is a semiconductor switch. It's a MOSFET. It's actively monitoring the current thousands of times a second. The moment it sees a short, say, in the heated passenger seat, it opens the circuit in microseconds.
Before the voltage on the main power bus even has a chance to dip?
Correct. It amputates the infected limb instantly to save the patient. It keeps the voltage rock solid and stable for the critical loads, like the steering and braking computers.
Okay, now let's talk about that steering motor itself, because adding redundancy there creates a really nasty physics problem.
Heat.
Heat.
It's all about heat. The modern solution is the dual winding motor. To be fail operational, you don't bolt 2 separate motors onto the steering column. That's too big and heavy. Instead, you take a single motor housing, and inside it, you wind 2 completely separate sets of copper coils. You have 2 separate control boards, 2 sets of power electronics, bolted to the same housing.
So you've effectively crammed double the electronics into the same small metal box.
Which means you now have double the heat density. And here is the enormous risk: thermal propagation.
If System A, the primary system, is working hard and starts to overheat,
It heats up the entire motor casing. System B, your backup, is sitting just millimeters away, soaking in that heat.
so if System A gets hot enough to melt the insulation on its windings or fry its own control board,
It could easily cook System B at the same time. And now you've lost your redundancy. You have a common cause failure that's caused purely by physical proximity and heat.
So thermal management is no longer just about performance or comfort. It becomes a safety-critical discipline.
It's not just about adding bigger cooling fans anymore. It's about rigorous thermal simulation. Can we mathematically prove that a fire in coil A will not functionally kill coil B for at least 30 seconds, long enough to perform that MRM?
This leads us perfectly into part 4 of the report, validation. How in the world do we test all of this? The report calls it the Euro NCAP 2026 CLIF.
It is a CLIF because the scope of testing that's required is exploding exponentially. The new protocols that are coming require verifying over 1,200 specific test scenarios.
And we are not talking about, does the self-park feature work? We're talking about high-speed failure scenarios.
At 130 kilometers per hour, you cannot test these on public roads. It's far too dangerous. And you can't even test all of them on a traditional proving ground anymore because of the phantom problem.
The phantom braking issue. I was reading that Percive AI case study in the source material. It specifically mentioned tunnels.
Tunnels are an absolute nightmare for radar systems. You have smooth, parallel concrete walls, you have ceiling lights, you have big metal ventilation fans. Radar waves just bounce off everything.
It's called multipath propagation.
Exactly. And sometimes the radar sees a reflection of a spinning ventilation fan on the ceiling, but because of a weird multipath bounce, its internal math calculates that the object is stationary and right in the middle of your lane.
So the car thinks there is a parked truck in the tunnel and it slams on the brakes.
Which is, potentially the most dangerous thing it could do. It could cause a massive pileup behind you. To fix this, you need really advanced signal processing. Specifically, you need better elevation data in the radar returns to know the fan is on the ceiling, not on the road.
But how do you test that fix? Do you just drive through every single tunnel in Europe 1,000 times?
You can't. It's impossible. So we have to shift our entire validation strategy towards virtualization. SIL, HIL, and VALIL.
Okay, let's decode that alphabet soup for the client. SIL is software in the loop.
This is pure cloud simulation. You take the actual production code, the binary that's going to be flashed into the car's ECU, but you run it on a server and feed it completely virtual sensor data. You can run 1 million different tunnel scenarios in an afternoon on AWS or Azure.
But pure software simulation can miss hardware-specific glitches. It doesn't know about, say, a voltage drop or electromagnetic interference.
That's why the next step is HIL hardware in the loop. Now you take the real steering ECU, the real brake ECU, and you bolt them to a test bench in the lab. You wire them all up, and then you connect them to a fault injection rig.
This is the torture chamber.
It really is. You program a machine with tiny robotic probes to physically short-circuit pins on the microprocessor. You use electronic switches to cut wires in the harness, and you have an oscilloscope measuring the response. Does the software successfully detect the fault and switch to the backup system in less than 100 milliseconds? Does the power supply stay stable? You are proving the physical robustness of the system.
And finally, there's VL, vehicle in the loop.
This is the holodeck for cars. You take the real physical car and you put it on a dynamometer, a rolling road, inside a big warehouse. But you trick its sensors. The cameras and radars are being fed data from a giant screen or a VR headset, essentially.
So the car thinks it is driving through a rainy night in Tokyo, but it's actually stationary and dry in a lab in Detroit.
Precisely. This allows you to safely and repeatably test the most dangerous scenarios, like a child running out into the street from between two parked cars, without ever risking a real child.
And speaking of children cyclists, the VRU, the vulnerable road user testing, is getting incredibly sophisticated. AB Dynamics has this soft bicycle 360 dummy.
Right.
Why do we need a special bicycle dummy? Can't we just use a cardboard cutout of a bike?
Not for the radar. Radar relies heavily on the Doppler effect to classify objects.
Yeah.
A static cardboard cutout doesn't move like a real bike. The soft bicycle 360 has wheels that actually rotate as it moves.
Rotating wheels on a test dummy.
Yes. The radar can see the micro-Doppler signature of the individual spokes spinning around, and that signature tells it, aha, that is a bicycle, not a shopping cart or a trash can. It even has articulated legs that pedal realistically.
So the car's perception system can actually distinguish between a static object and a pedaling cyclist based on the signature of their leg movement.
Yes, that's the level of fidelity required now. And we have to test that the fail operational system can maintain that correct classification, even if, say, one of its forward-facing radar sensors fails.
The amount of data you must be collecting here it's staggering.
It's a data tsunami. A single L4 development vehicle with LiDAR, radar, and high-res cameras generates about 500 terabytes of raw data. per
You
day.
cannot upload that to the cloud. The bandwidth simply doesn't exist.
So we need smart logging. We need to put edge computing inside the data logger itself, in the trunk of the car. It has to monitor the data stream in real time. If you're just driving on a straight, empty highway and nothing is happening, it just deletes the data.
It only saves the oh no moments.
Exactly, the edge cases,
Right.
the near misses, the moments the human safety driver had to take over. That is the high-value data you need to find and ship back to the cloud to retrain the AI perception models.
Okay, let's move to part 5, the broader ecosystem. We need to loop back to the energy source for a moment. The battery.
The battery is the heart of the EV. If the heart stops, the brain dies instantly. For a fail operational vehicle, we are now seeing a demand for no thermal propagation at the battery pack level.
We talked about this concept with the motors, but with batteries, it's really about fire.
It is. If a single battery cell goes into thermal runaway, if it catches fire, the pack must be designed so that the fire cannot spread to the neighboring cell. But it's more ambitious than that. The pack must be designed so that even if an entire module is actively burning, the remaining healthy modules can still deliver stable 12-volt power to the steering and braking systems for at least 15 minutes.
That is a massive engineering challenge. To keep a burning battery live and functional.
It requires advanced isolation materials, intelligent venting strategies, sophisticated battery management systems. But it's becoming a requirement. You cannot lose steering just because one battery cell out of thousands failed.
And to manage the health of this critical component, we are starting to see the concept of battery passports.
Yes, from companies like AVL and Tributech. This is essentially a digital twin for the battery. It's a secure digital record that tracks the battery's health and history from the moment the lithium is mined, through the factory, and throughout its entire life on the road.
Why does this help with safety?
It's all about predictive maintenance. If the digital twin, which is running in the cloud, sees a worrying trend, say, a slight but steady increase in the internal resistance of Module 4, it can predict a potential failure weeks or even months before it happens.
And the car can warn the driver.
The car can pop up a message, service required, redundancy system compromised. It turns a potential roadside emergency into a scheduled, routine maintenance event.
Now, I want to touch on something a bit controversial that was mentioned in the report, the ASIL-E debate.
Ah, yes. The theoretical frontier. So right now, the ISO 26262 standard for functional safety stops at ASIL-D. That's the highest level of rigor. It corresponds to a failure rate of less than 10 FATs, which is 10 failures in time per 1 billion hours of operation.
Which is incredibly reliable.
It is. But for true driver-out scenarios, level 4, level 5, where there is no human at all, some experts are arguing that even ASIL-D is not enough.
They're proposing a new, even higher level, ASIL-E.
Right, which doesn't officially exist yet. But the idea is that it would demand even higher levels of diagnostic coverage.
What kind of numbers are being thrown around?
We're seeing proposals for 99% diagnostic coverage at a frequency of 50 hertz.
Okay, translate that for us.
It means the car's safety systems must check their entire nervous system, every critical wire, every chip, every line of safety code 50 times every second. And in those checks, it must be able to detect 99% of all possible latent faults instantly.
That's faster than a human can blink.
Much faster. It effectively means the car has to be completely self-aware of its own internal health in hard real time.
Before we close out, let's just quickly look at the geopolitical map. We have this core technology, but the implementation strategy varies quite a bit by region.
It's a real divergence. In China, they are pushing very hard on the vehicle road cloud integrated strategy.
Infrastructure as redundancy.
Right. They are putting sensors, LiDAR, and 5G communication units on streetlights and highway gantries. So if the car's own sensor fails or is blocked, the smart city infrastructure can tell the car, warning, there is a pedestrian about to cross from behind that bus. It offloads some of the redundancy costs from the vehicle to the government infrastructure.
And what about the U.S.?
The U.S. approach, which is really led by companies like Tesla and Waymo, is all about commercial data dominance. They believe that if you collect enough petabytes of real-world driving data, your AI can develop something akin to common sense.
So even if a sensor fails, the AI can infer the road geometry or the likely path at other cars from what remains?
Exactly. It's a very software-heavy, AI-centric approach.
And Europe remains the skeptical regulator.
Europe is the hardware fortress. The strategy there is high-spec sensors from the start. LiDAR is often seen as mandatory, not optional, and every component must be rigorously verified against the standard. It's a slower, more expensive approach, but it creates a very robust, trustable product from day one.
So we've reached the outro. We need to summarize our report for the client in that boardroom. What's the final deliverable?
The core conclusion is this. The winner in the 2026 automotive market will not be the OEM with the flashiest AI demo or the biggest infotainment screen. It'll be the one with the most robust and resilient digital nervous system.
It's a fundamental shift from component quality to system resilience.
Correct. You could have the best, most expensive LiDAR in the world, but if the Ethernet switch that connects it to the brain lacks FRER redundancy and fails, the whole system is worthless. It's trash.
And for that individual engineer listening to us right now, what is their personal takeaway?
Stop thinking in silos. Please stop thinking, I designed the wiper motor. You have to start thinking, if my wiper motor shorts out, does it cause a voltage sag that could reboot the steering controller? You are part of an interconnected survival web now.
The era of the blue screen of death is over. In a car doing 130 kilometers an hour, there's no reboot.
No reboot. Only seamless degradation to a safe state.
I want to leave the client and our listeners with one final provocative thought. We've just spent an hour outlining a system with dual motors, dual batteries, dual ECUs, smart fuses, LiDAR, radar, cameras.
It is an incredibly complex and expensive bill of materials.
So are we designing cars that are simply too complex to be economically viable to own and maintain? If a minor fender bender now requires replacing a dual-winding motor, recalibrating 2 radars, and recertifying a secure gateway.
The repair bill could easily total the car.
Exactly. The OPEX, the operating expense of maintaining these fail operational fleets, might be the thing that kills the business model. So how do we balance this absolute need for safety with affordability?
That is the multi-billion-dollar question. And perhaps the industry will eventually realize that a theoretical ASIL-E is just too expensive, and we have to find a clever middle ground. But for now, for the 2026 timeframe, the mandate is clear. Build to be redundant, or don't build it at all.
A sobering conclusion for the roadmap. Thank you for joining us on this deep dive. And to our engineering listeners, good luck with the architecture.
You're definitely going to need it.
Drive safe, and we'll see you in the next one.